This is a very important section for your exam, at least your information for your quiz as well. On acid-base balance, I did notice that some things were a little confused in what you put on your study guide. So I want to go through the study guide and make sure that you understand everything. We'll be taking a look at some of the things in the text and make sure that while the quiz is still open after you've taken it, that you go back through and write down the answers to the questions if you missed any, because that's very, very important information. And I think that you will learn much from those questions that you might have gotten wrong as well. All right, so in section 7.4, we want to go over what is the role of the nephron in acid-base balance. Take a look at what the intercalated versus principal cells. This is principal spelled wrong. It should be an AL. And then what happens when we are in an acid-base imbalance, like metabolic or respiratory acidosis and alkalosis, and how we fix the problem. So let's just go right into what an acid-base imbalance might happen to be. So your body at various times is going to produce acids, and typically your body has the ability to withstand that production of acid. And so in this case, what is hydrogen ion in acid-base balance? Well, hydrogen ions are what produces the pH of a solution. And so if you increase the concentration of hydrogen ions, the pH will drop. If you decrease the concentration of hydrogen ions, then the pH rises, because pH is just simply a relative concentration of how many hydronium ions, how many hydrogen ions are in water. So water, as you know, is H2O, and what water molecules are going to do is separate into an H and an OH. So if you do something to increase the number of hydrogen ions, then the pH drops. And if you increase the number of hydroxide ions or OHs, or take away hydrogen ions, then the pH is going to rise. So there's two kinds of acids that we can have causing this acid-base imbalance. Volatile acids. Volatile means that it will become a gas. And so how are they removed? Is that respiration is going to remove them. So carbon dioxide. Well, there's no hydrogen ions in carbon dioxide. And I put, yeah, I know there's no hydrogen ions. But what happens, we'll take a look at the carbonic acid bicarbonate equation, and then I'll show you how carbon dioxide is an acid. But the volatile acids like carbon dioxide must be exhaled to be removed. The non-volatile acids are going to be eliminated by the kidney. And so these acids are going to be produced through our metabolism. Take, for example, anaerobic respiration. So when we don't have oxygen to produce ATP, we're going to have acidic byproducts, and because we have no proton acceptor. Oxygen isn't our proton acceptor, and so therefore we do lactic acid fermentation, and so we will be these protons, or these hydrogen ions, will be given off and decrease the pH. So they'll be secreted or filtered by the kidney. Okay, so there are three lines of defense in maintaining our acid-base balance. What are those three lines? Well, the first one are the chemical buffers, and I neglected to put in here what the chemical buffers are. So I'm going to go ahead and just type that in right now while you're watching it. So we have three chemical buffers. They are bicarbonate, carbonate, which is the extracellular fluid buffer. Then we have phosphate, which is the intracellular fluid buffer. And then, let me make this bigger. Wow. Okay, intracellular fluid buffer, so within the cells, and then protein. And those are our three chemical buffers. And bicarbonate will only be in the plasma and the extracellular fluid. Phosphate will be intracellular, and it will also buffer the urine, which we will get to, and then proteins. Now, proteins are interesting because they have an amine on one end and a carboxyl group on the other end. And so amines can be bases and carboxyls can be acids. And so the amine group will accept hydrogen ions to raise pH, and the carboxyl group will donate hydrogen ions to lower the pH, depending on how you need to buffer a solution. We'll get more into what buffers are for in just a minute. So then if the chemical buffers, because there's a limited amount of chemical buffers in your body at any one time, and they can easily be overwhelmed if you are in a very drastic acid-base imbalance. And so we need to have two other mechanisms that will compensate for our pH being thrown off, respiratory mechanism and our renal mechanisms, or our kidney. The respiratory mechanisms are going to come second because they are very rapid. Our breathing rate will change very rapidly and can cause a great amount of compensation for a change in our pH. And the renal mechanisms, though, take hours to days in order to kick in, so we may be in an imbalance for quite some time before the kidney will be able to do the things that he needs to do to fix the problem. And so it'll go in that order. As our pH changes, chemical buffers that are automatically right there will try to stop the pH from changing too drastically, and then respiratory system, and then renal mechanisms. All right, so the normal pH range of our blood should be between 7.35 and 7.45. We're okay. 7.4 is where it's supposed to be, slightly alkaline. But we're okay if we are on either side of 7.4 like that. If we have a pH of our plasma that is less than 7.35, then we're considered acidosis, even though we are not into the acidic end of the pH scale. We are still in what we call physiological acidosis. And then alkalosis is if the pH is greater than 7.45. Okay. Oops. Okay, where's my, oh, I gotta stop doing that. Okay, there we go. Oh, well, there that is. I'm gonna get rid of that now. Okay, because it's not gonna go with that, dang it. Okay. All right, so then what are buffers? So buffers are chemicals that either donate or accept hydrogen ions or hydroxide ions, but we don't worry about that in our bodies, in order to keep the pH of a solution from fluctuating wildly. Okay, so the extracellular fluid buffer is the bicarbonate buffer system, and I just put a little note there. My on-campus students here at EA know that my favorite equation, my favorite reaction of all time is cellular respiration. And my second favorite reaction is the carbonic acid bicarbonate reaction. And here it is. So notice it is a reversible reaction. It's going to proceed in both directions based on what is the amount of the reactants. And so if you have more reactants, if you have more CO2 and water, then it will drive the reaction to the right. But if you have more hydrogen ion and more bicarbonate, oh, that should have a negative charge on there, you guys. Oh, sorry about that. So bicarbonate is HCl3 minus. Oh, I'm so sorry, I didn't do that. Oh, I didn't do it over here either. Oh, you guys, I didn't do it anywhere. Okay, bicarbonate is an anion, so make sure you know that. Oh, this is horrible. But anyway, if you have more hydrogen ion, more bicarbonate, then it will drive the reaction to the left. So I put that right there. Depending on which side you have more reactants, the reaction will be pushed in the opposite direction. Okay, so we want to look at, well, when would you have more over here and when would you have more over here? So we're going to start with the CO2 and water. So these are the products of cellular respiration. So whenever your cells are going through cellular respiration, they produce CO2 and water, and that CO2 and water, in order to get rid of the CO2, is going to form carbonic acid. It'll form it naturally, but it's a really slow reaction. Instead, we have an enzyme called carbonic anhydrase that we find in our red blood cells, as we talked about before with CO2 transport, but we also find it in the kidney, and we'll talk about the importance of carbonic anhydrase in the epithelial cells of the kidney tubule later on. And so in the presence of carbonic anhydrase, CO2 and water are going to be converted to carbonic acid, and carbonic acid, being an acid, will dissociate in water and give you hydrogen ions and bicarbonate ions. It's a weak acid, and so it doesn't completely dissociate in water. So when you put carbonic acid in water, some of the molecules will be present like this, and some of them will be split up, dissociated like that. Okay, so in our tissues where we're producing CO2 and water to form bicarbonate, that will drive the reaction to the right. Okay, so in the tissues, this reaction goes to the right. So I put that right there. It will drive the reaction to the right, and hydrogen ions and bicarbonate will be carried to the lungs and the bloodstream. Remember, hydrogen ions are going to bind to hemoglobin once oxygen has left, or it's actually going to promote O2 unbinding in the tissues, and so then you have deoxyhemoglobin. So hemoglobin will be bound to the hydrogen ion, will sit in the red blood cell until we get to the lungs, and then remember this bicarbonate is going to leave the red blood cell in the capillaries of the tissues, and then do the chloride shift. So chloride ions will come in and bicarbonate will go out into the plasma so that it can do what? Buffer the plasma. Whoa, it's always so fun for my students when we talk about, you know, this as far as respiration, and they're like, well, why would you want it to leave the red blood cell? Why do you need to have chloride come in and have bicarbonate go out? And then when we get to this, because this is right at the end of the semester, then they're like, oh, that's really pretty awesome. Okay, so then once your blood gets to your lungs, now you have lots of hydrogen ions and lots of bicarbonate, and that will drive the reaction to the left. So remember, this reaction goes to the left in the lungs. And so that's how my kids remember it. Left lungs, and then it's tissues right, which doesn't go, but at least left and lungs goes together to make that volatile CO2 that you can then exhale. So what are the other buffer systems in our body? I think they meant, this is instead of respiratory and renal, the phosphate buffer system that we have intracellularly and within the urine, and then the protein buffer system that we have within our bloodstream, at least in the plasma, not in the interstitial fluid, because remember there's no proteins in the interstitial fluid, because that would mess up the osmolarity of your blood. So in your plasma, all the plasma proteins, albumin, antibodies, whatever's out there, those can buffer the blood, and then inside of the cells as well, the proteins that are inside of the cells. So, but no protein buffering out in the interstitial fluid. Okay, so then respiratory system, how is that going to regulate the pH? Okay, so the rate of breathing will either increase the pH by hyperventilation, and as we blow off CO2, okay, so as we blow off CO2, breathing out, we're driving this reaction this way because we're losing this, and so we're going to have the bicarbonate in greater amounts, so we'll drive the reaction to the left, and we'll lose these hydrogen ions because now they're not going to be free anymore, they're going to be bound up in water. And so now our pH is going to rise because we took the hydrogen ions out of solution. Hypoventilating, though, because we're not blowing this off, this is going to build up and drive the reaction to the right. And now we're building up all these hydrogen ions, which is going to drop the pH. So remember, hyperventilation will raise pH, and hypoventilation will lower the pH. How quick is this response? It occurs within minutes. And I love, this is one of my favorite things. I always wait all semester long to do this with my students. I'm a fairly short person. I'm just barely over 5 feet. And so, yes, I try to compensate by wearing 4-inch heels in my lectures. So my heels are always very high. And so it's really hard to do wall sit in high heels. And so I'll sit against the wall. You know, I won't be sitting on a chair or anything. I'll just be wall sitting. And that's a very anaerobic activity. Your amount of ATP requirement is quickly going to exceed what is supplied by aerobic activity. And so you're going to go into lactic acid fermentation. You're going to glycolysis is really all you're going to do. So now as I'm doing that, I'm going to go into oxygen debt, and I'm going to start hyperventilating, and because my pH is dropping, I'm going to start hyperventilating. And so we time how long it takes me to start breathing heavy. And so when I do start breathing heavy, that's when I'm in a little partial, just for a few moments, but not forever. I'm in metabolic acidosis. So anywhere between 45 seconds and a minute 15, depending on the day, depending on my energy level that day and how much I've been working out or whatever. But yeah, so whenever I start breathing heavy, that's when my respiratory buffering mechanism has kicked in. So what's the limitations of this system? With the chemical buffer system, the limitations are great because we just don't have all that we need. And so we can use up those very, very rapidly, and then the respiratory system will kick in. And respiratory works really good for most situations. Most of the time you're going to stop whatever you did that put you into acidosis. But what if you're in diabetic ketoacidosis, for example, and you are just seriously in metabolic acidosis? You're going to start hyperventilating to do that. But if you hyperventilate too much, you probably know what happens if you hyperventilate too much. You blow off too much CO2 to stimulate your ventral respiratory group to get you to, or at least to produce hydrogen ions to stimulate your central chemoreceptors to get your ventral respiratory group to fire. Your dorsal respiratory group to fire. So you'll pass out. And then conversely, if you hold your breath because you're in metabolic alkalosis, because you've been vomiting or you're constipated or some other metabolic cause to be in alkalosis, again, you're going to pass out. So it's when your CO2 levels change drastically enough that your brain goes, okay, I really hate this and I'm going to take over, and then you'll go back to normal breathing. So those are the limitations of that. Okay, so kidneys. Explain how the kidneys regulate the body's pH and compensate for elevated hydrogen ion or bicarbonate. So we're going to go ahead and go to the textbook and just kind of switch back and forth between that. So I'm hoping at this point that you can see the textbook. So I'll go back and I won't know till this is over. All right, we should still be, now I'm gonna stop this and share it again. Screen two, yeah, we were just fine. Okay, here, if we just read through, I wish that it would, my computer would highlight it, but I'm not that tech savvy. I couldn't figure out how to do that. Okay, so what's going to happen? Well, first of all, limitations to this buffer system? No, there are no limitations to the kidney's buffering ability. However, because there's always the however. So under normal circumstances, your kidneys are going to buffer forever, and you're going to be good. But let's say that you're in diabetic ketoacidosis, for example. No, that's a bad one. Let's say that you are that you have COPD. That's a better one. You can't breathe. You're retaining CO2. Your pH is dropping. And if you are consistently in that state, you may have some problems as a result of it. We will die from too excessive change in pH, which we'll look at in a chart later on. So obviously that's when your kidneys stop. But otherwise, there are no limitations. The kidney can do everything that it needs to buffer you the pH. And how quick is this response? That's the problem, is that it takes hours to days in order for it to make up the difference. So you may be feeling pretty bad for a while, like with diabetic ketoacidosis, before you're going to feel better. Okay, so anyway, let's go to here, and here is how it's going to do. Of our 3 lines of defense, urinary system is the only one that can restore all of the components to their normal values. It does this by either excreting or absorbing bicarbonate ions and hydrogen ions, or through the production of new bicarbonate. Okay, so let's say that you're in acidosis. So you want to get rid of hydrogen ions. So we can excrete the hydrogen ions, or we can reabsorb bicarbonate, or we can produce new bicarbonate. We'll take a look at that, because remember I said the kidneys have carbonic anhydrase, so that's why they can do that really rapidly. Conversely, if we're in an alkalotic state, what we want to do is drop the pH, so we want to retain hydrogen ions, and we want to excrete bicarbonate. Okay, so the kidney is also responsible for excreting the non-volatile acids, so like the lactic acid and other organic acids that we produce in the body each day. let's see, hours to days. So what are we going to do to regulate acid-base balance? We must reabsorb all of the bicarbonate that's filtered each day. And we'll look at how that happens in the proximal convoluted tubule cells. But yeah, we need to reabsorb all the bicarbonate first. So it's going to be freely filtered, but we have to bring it back in again. So in the kidney tubules, the carbon dioxide will react with water in the presence of carbonic anhydrase, like I said, resulting in hydrogen ions and bicarbonate. So the hydrogen ion is secreted into the tubule for the exchange of sodium. So we have a hydrogen ion, potassium, or not potassium, hydrogen ion sodium exchanger. Oh, it's got a name. I can't remember what it is right now. But whenever we secrete, well, whenever we reabsorb sodium, then we're going to secrete hydrogen ions. And then once in the tubule, the hydrogen ion will combine with filtered bicarbonate, converted to be carbon dioxide and water, and then carbon dioxide diffused back into the tubule cell, combined with water again, hydrogen ions and bicarbonate. So it's a nice little cycle thing going on. And then the bicarbonate will be released or reabsorbed into the blood. So under normal conditions, then virtually all of the filtered bicarbonate can be reabsorbed back into the blood. So proximal convoluted tubule, here is that happening right there. So here is the sodium hydrogen antiporter. Yay, I knew I would remember. So this is an antiporter. So whenever we reabsorb sodium, we are going to excrete hydrogen ions, but now these hydrogen ions are going to combine with the bicarbonate that we just filtered, because we don't have bicarbonate pumps or bicarbonate exchangers, and so we have to turn it back into something that will automatically go into the tubule cell. So the hydrogen comes out, combines with the bicarbonate that we filtered, turns it back into carbon dioxide and water. The carbon dioxide diffuse it, and the water diffuse back into the cell, and then the carbonic anhydrase that we have within the proximal convoluted tubule cell will change this back into bicarbonate, and then we have the symporter. Not an antiporter, but we have a symporter here, where as we absorb sodium, now the sodium wants to go into the paratubular capillaries, and the bicarbonate will go with it. Oh, it's a beautiful thing. Oh, you guys, I can't even tell you how much this excites me. I should have been a nephrologist. Okay, so that is what we did. So let me put this back over here. So take a look at what's happening in the proximal convoluted tubule, how the sodium is an antiporter for hydrogen ions, and then a symporter for bicarbonate. And what's reabsorbed by the blood? Bicarbonate. What's excreted? Hydrogen ions. Where does this buffering take place? In the proximal convoluted tubule, which cells are, well, in the blood, actually. When we put the bicarbonate in the blood, and then which cells are involved? The cells of the proximal convoluted tubule. All right, if the body needs to absorb hydrogen ions and secrete bicarbonate, how does it do that? So let's take a look over here. This one, right, oh, just remember I told you that the kidneys can also produce new bicarbonate because they have carbonic anhydrase. Excuse me, so any bicarbonate or carbon dioxide in the blood that diffuses into the tubule cells will oh, I just lost my thought, will be changed into bicarbonate, and then we can reabsorb it that way if we need more. Okay, so now let's go into this other part. So other important functions of the kidneys pertain to their ability to either excrete hydrogen ions while reabsorbing bicarbonate, or excrete bicarbonate ions while reabsorbing hydrogen ions. The newly formed bicarbonate can then buffer the non-volatile acid. In the collecting ducts of the nephrons, okay, so we're here in the collecting ducts. There are two types of cells. There are type A intercalated cells, and then type B intercalated cells. And so we'll look at that. But here is the important thing right here. Type A cells secrete hydrogen while absorbing bicarbonate, and the type B cells, or the beta cells, are going to absorb hydrogen ions when secreting bicarbonate. So type A cells will be active in acidosis. B cells will help in basosis, but we don't call it that, alkalosis. So I don't know if they if they meant to do it that way, I mean, type A stands for alpha. So these are alpha intercalated cells and beta intercalated cells. But that's how it works. So when your body's in acidosis, then the alpha cells work. And when you're in alkalosis, when your body's too basic, then the B cells are going to work. So keep that in mind. All right. Okay, so here, let me just read through this, and then we'll take a look at the picture again. So if you take, you'll notice there's a difference in the location of the carriers, and that will determine if the cell is active in the in maintaining the pH of blood. So in acidosis, the cells that secrete hydrogen ions are active, while in conditions of alkalosis, the ones that reabsorb hydrogen ions are active. So these are alpha cells and then the beta cells. Notice, and this is really important, that as hydrogen ion is moving across the membranes, potassium is moving in the opposite direction. So we're going to end up in either acidosis or alkalosis. We're going to end up with hyperkalemia or hypokalemia, and we'll get into putting those together right now. All right, so when we have acidosis, when we're excreting hydrogen ions because we're in acidosis, we're going to end up with hyperkalemia. And then we're in alkalosis and we're retaining hydrogen ions, then we're going to secrete the potassium, and then we'll go into hypokalemia. Okay, in both of those cases, we're going to affect membrane potential. And here's how I just remember it. When we're in hyperkalemia, we are hypopolarized. And then when we are in hypokalemia, in our interstitial fluid in our blood, then we are hyperpolarized. So then you can think of, you would be in spastic contraction, in hypokalemia, and then paralysis. You're going to get paralysis on both of them, but are you going to get spastic, or are you going to get flaccid? So flaccid and hyperkalemia, and spastic and hypokalemia. Okay, so then either condition can have tragic effects due to their membrane potentials. Your heart can go into arrhythmia and die, and so we don't want bad potassium levels. And then remember, it is important that excreted hydrogen ion be buffered in the urine. This is accomplished by phosphate buffer or by ammonia. Okay, so let's take a look now at these cells. Okay, so in your study guide, it says if the body needs to absorb hydrogen ions, secrete bicarbonate, how does it do that? Which cells are involved? They are the beta cells. So we are absorbing hydrogen, because what we're going to do is kick out the potassium, and we're going to absorb hydrogen ions. And so here we are kicking out the potassium and absorbing the hydrogen ions. And how did we do that? By taking the CO2 out of the bloodstream, converting it to bicarbonate, and then sending it out by the chloride shift. Okay, so the same chloride shift that we had happening in the red blood cells out in the tissues when we pick up CO2, we're going to do that same chloride shift, but instead we're kicking the bicarbonates out into the lumen and then out in the tubule, and then we'll excrete it. Okay, and then how does the body buffer acidic urine to reduce damage to the kidney tubules? That will be phosphate. Okay, and then here is, let's look at this one, because it doesn't have the type A cells all of a sudden. But anyway, so here is, well, what if we're acidic and we need to get rid of hydrogen ions? So here's the hydrogen ions getting kicked out, and the potassium's coming in. And as the hydrogens get kicked out, urea, that's ammonia, and then it becomes ammonium. Will be in your urine from protein metabolism. Here's some phosphate that's in there too, and it'll grab onto those hydrogen ions. Look again, get that nice little chloride shift. So the chloride from the bloodstream is going to go into the tubule cell, and the bicarbonate that was made from this CO2 then will pass back into the bloodstream. So I love the kidney is the best thing ever. Okay, so let me put this back. Okay, how does arterial pH impact this buffering process? What are the intercalated cells and what do they do? So low pH, then, so here basically is this graph. So low pH is the alpha intercalated cells, high arterial pH, the beta cells. So we're in acidosis here, alkalosis here. Principal cells, just the bicarbonate in the tubule to reabsorb that. Was the function secretion of hydrogen ions, secretion of bicarbonate, reabsorption of filtered bicarbonate. Any hormones that affect this? Aldosterone, you know, just with the hydrogen ion, the sodium exchange, but really not so much over here, but aldosterone would affect sodium transport. How are they transported? We just went over that. See the diagrams. Okay, this is really important because I did see some people have this backwards. So when the alpha cells, okay, when the alpha cells are activated, it makes the pH of blood more basic by reabsorbing bicarbonate into the blood and secreting hydrogen ions. And then conversely, when the beta cells are working, we are lowering the pH. We're making it more acidic by reabsorbing hydrogen ions back into the blood and secreting bicarbonate. And then this is just slightly basic, but we're just trying to maintain homeostasis here by reabsorbing all the bicarbonate and secreting hydrogen ions. There's the role of potassium, so I already went over that, so you can take a look at that. Okay. So now there's some stuff that I want to show you. I did not fill this out, and the reason, well, I'll tell you why in a minute. Okay, so acid-base disturbances. I wish that they were teaching you how to do arterial blood gases. I'm kind of going to go over that a little bit, but you'll have to do, if you guys are going into nursing school, you will spend a lot of time second block. Well, it's second block here. I don't know where it is at BYUI or wherever you're going, but you will spend a lot of time trying to figure out arterial blood gases and what acid-base disturbance your patients are in, and then what kind of compensation your body is trying to do for that. So I make a very concerted effort to teach my students how to do ABGs before they get to the nursing program, and then I have a kid that's in emergency medicine. He's doing his residence in Kingman, Arizona, and he came to visit me when he graduated med school and said, "Oh, Mrs. G, this was all I remember is ABGs." And he says, "I can't tell you how many times in emergency medicine you have to know how to do ABGs." So, so that's what this is all about. Okay, so this was wrong. This said acidosis again in my copy, so I just fixed that, but maybe because I messed something up, I don't know. But anyway. So when your acidosis should be less than 7.35, when your alkalosis should be greater than 0.45. Causes, which we'll get to in just a minute because they are numerous, depending on whether we're talking about respiratory acidosis or metabolic, and the same with the alkalosis. Result on the body, acidosis, if we drop below 7, you will go into a coma and die. If you go above 7.8, I think it is, I think we can go all the way to 8 before bad stuff happens. Tetany, convulsions, and death. So we're going to die if our pH is too extreme. So here are the normal ranges. Normal PCO2 should be between 35 and 45 millimeters of mercury. If you're in respiratory acidosis, then your pH is greater than 45. You are retaining, oh, that should be a little g. You are retaining carbon dioxide, which is making everything acidic. And then if it's less than 35, then you're blowing off CO2 and it's taking hydrogen ions with it, and therefore your pH is rising. Metabolic acidosis, or the metabolic numbers are based on bicarbonate levels within your blood, should be 22 to 26. I know it said below 24, above 24, but you're still in a normal range, you guys, like at 23 and 22. So I'm giving you the accepted range than what was in your text. So if you have a bicarbonate level of less than 22 milliequivalents per liter, then we consider you metabolic acidosis, and greater than 26 milliequivalents per liter, we consider you in metabolic alkalosis. Okay, so staying in balance is critical. In order to achieve balance, the body will compensate for high or low values. All right, so how does the body compensate for respiratory disturbances? So anytime that respiratory is the cause, either because you have COPD and you're retaining carbon dioxide, or you're hyperventilating and you're blowing off too much CO2, your kidneys will fix the problem. How does your body compensate for metabolic disturbances? Well, that means that you've got something that's producing too many hydrogen ions, or you're a loss of hydrogen or a gain of bicarbonate. So our respiratory mechanisms will fix the problem. Now, okay, I didn't fill this out primarily because, well, okay, I guess we can't. Well, I know, I'm going to do this. So I'm going to go ahead and type something in here. So if when we're in respiratory acidosis, then we're going to be less than 7.35. Whoops. 0.35. Okay, this is going to be greater than 45. Oops. 45 millimeters of mercury. And our bicarbonate would be normal. I mean, you know, if it's compensating, then it will be high if compensating. Compensating. Okay, so above 26. Oh, let's put that. That's better. So we'll put greater than 26 mil equivalents per liter if compensating. Okay, and then respiratory alkalosis is greater than 7.45, and my PCO2 is going to be less than 35 millimeters of mercury, and my bicarbs were going to be less than 22 mil equivalents per liter if compensating. Okay, so the pictures of causes and symptoms, you know, I like the little pictures that they had. Respiratory acidosis, as far as my students know, it's going to be COPD. So anything that's going to impair breathing. So impair CO2 elimination. Typically, it's going to be chronic bronchitis and emphysema, cystic fibrosis, maybe pneumonia, maybe some asthma. It all depends on any condition that impairs gas exchange or lung ventilation. If we have increased airway resistance, like we have in asthma, or decreased expiratory airflow leading to retention of CO2. And that's the thing, is that we have too much CO2. It may be caused by rapid shallow breathing, but who does that? There's no pathology for rapid shallow breathing. So, but yeah, as long as CO2 is being retained. And then you could have a narcotic or barbiturate overdose. Barbiturate? Oh, it is barbiturate. Oh, I've been pronouncing that wrong for 40 years. Overdose. Barbiturate. Oh, huh. Okay, or injury to the brainstem, or injury to the brainstem. So depression of your respiratory centers resulting in hypoventilation and respiratory arrest. Okay, so that's going to be respiratory acidosis. Respiratory alkalosis is always hyperventilation. And again, oops, there's no pathology. There's no disease that makes you hyperventilate. But maybe you're hyperventilating at high elevation. Let's see, anxiety. Oops, anxiety. Pneumonia. But just because you have pneumonia doesn't mean you're going to hyperventilate. Okay, asthma maybe too. Asthma. Okay, but remember, there is no pathology for respiratory alkalosis or brain tumor or injury. We can also put that brain tumor. Anything that's going to affect your respiratory centers and cause you to breathe too much. Brain tumor or injury. Okay, so there's those. How does the body compensate? How do the lab values change? Okay, so if you're in respiratory acidosis, so then what you want to do is that your kidneys will do three things. Oops, kidneys secrete H+, so your hydrogen ion values in your blood will drop and will rise, and your hydrogen ion values. Your pH in your blood will rise and your pH of your urine will drop. Reabsorb bicarb or make new bicarbonate. Okay, so what does the body do here? Kidneys, kidneys retain hydrogen ions or excrete bicarb. Okay, all right, so metabolic acidosis will be less than 7.35. Again, PCO2 levels will be less than less than 35 millimeters of mercury. If compensating, because now you're hyperventilating to fix the problem, and then your bicarbs will be less than 22. Okay, one thing that I always tell my students here is that acidosis is either a gain of hydrogen ions or a loss of base. So here can be a loss of base, and we'll take a look at that in just a minute. Okay, metabolic alkalosis, again, is anything greater than 7.45, though that never changes, regardless of what the cause is. PCO2 will be greater than 45 millimeters of mercury because you are retaining carbon dioxide to make conditions acidic, and this will be greater than 26 equivalents per liter. Okay, metabolic acidosis. This is the one that's got a ton. This is like the most common acid-base imbalance that you have. Okay, so severe diarrhea with loss bicarbs, because you didn't have a chance. Okay, so remember when you're, we're just getting into digestive system. So in order to neutralize the acid chyme coming from the stomach into the duodenum, we need to make that duodenum neutral again. And so your pancreas is going to pump a ton of bicarbonate into the duodenum, and you're supposed to reabsorb that. But if you're throwing that fluid through your digestive system way too fast, the bicarbonate will not be absorbed and you will lose it in your urine. Okay, if you have renal disease, if your kidneys are not able to do all that they're supposed to, can't get rid of acids formed by normal metabolic processes, let's put renal disease doesn't eliminate H's, okay? And then, whatever. Okay, then another one is DKA. Okay, so diabetic ketoacidosis, ketone bodies, bodies are produced when fatty acids are used as fuel. Okay, if you got no carbohydrates, if you can't metabolize carbohydrates, then you'll be using your fats as your energy source. Okay, and then essentially untreated diabetes mellitus or diabetic ketoacidosis is the same as starvation. And I'm just going to put DKA. Okay, what else? Okay, too much alcohol consumption. Because alcohol is converted to acetic acid. In order to neutralize it, we take it, we turn it into, or not neutralize it, that's a bad word, detoxify it. It's converted to acetic acid in the liver. Okay, high ECF potassium, because because they compete with hydrogen ions for secretion, so your kidneys are going to be kicking out the bicarb, not the bicarb, you're going to be kicking out the potassium, and then hydrogen ion secretion is inhibited. Okay, and that's good. All right, then if we come over to metabolic alkalosis, all right, so if severe diarrhea caused you to have metabolic acidosis, metabolic alkalosis will be caused by constipation and retention of too many bicarbs. We absorbed them all instead of getting rid of them. Vomiting. Oops, or gastric suctioning. Maybe the loss of hydrochloric acid. Okay, and then excess aldosterone. So, oops, too much reabsorb. Too much reabsorption of any poles. So remember, if sodium is being reabsorbed, then hydrogen goes into the urine, and then you will lose hydrogen ions, and so metabolic alkalosis. So alkalosis is a gain of bicarbs, but the loss of hydrogen ions. So now I'm losing hydrogen ions. And how else can I gain too many bicarbs? Eating too much Tums, eating too many Tums, or other bicarbonate rich stuff. Well, I didn't put that. So too many bicarbs. Ingestion, too many, bicarbs. Okay, so there you go. Oh, okay. So what are we going to do here if we're in metabolic? So then we go into hyperventilation to remove carbon dioxide to reduce hydrogen ion concentration. Okay, and then we will hypoventilation to increase CO2 and increase H+ in plasma. Oops. Okay. Oh. Okay. I think that's it. Take the quiz. There you go. All right. So here is the ABGs, but I took the quiz and I didn't see anything specifically on ABGs, so everything here is fine. So I'll save this. I'll post this, and you can take a look at that too and compare it to your study guide. And so good luck on the test this weekend, and then we'll wrap it up. I'll have some more videos on endocrine system. Endocrine system is one of my favorite and can be a little tricky too. Digestion should be pretty straightforward. So, so there that is for acid-base imbalance.